So let me begin by saying this is a great honor and a total surprise to me. I didn't know I was being considered for this, but Harvey Mudd meant a lot to me, so this is very important. And the title of my talk is The Quest for the X-ray Laser. This is the work that I've been doing with my wife for the last 20 or so years, and it's been a very interesting ride, and I'll tell you more about it. And just to think, I've been on a diet for the past couple months to look good for all you guys. Oh, well. So I'll tell you a little bit about why I do what I do, what my career path has been, and where I am today. And then I'll go into the work that we've been doing in lasers and X-ray lasers. And this work has resulted in the first tabletop scale devices that can be really called an X-ray laser. X-ray laser is in quotes here. I'll explain a little bit more about that. I'll also tell you a little bit about where this work is going. First, why did I do physics? Well, my mom enrolled me in a Saturday morning science class at age 4 where we were playing with Bunsen burners and all sorts of fun stuff. So I was a scientist from then on, reading lots of science fiction. I'm sure I have that in common with a large number of mudders. But really what excited me about physics was not sort of the wonder of the universe part of it, which is great, but it's the human adventure. It's through understanding the world that we can do more and advance our capabilities. And so I went into physics because it really explores the limit of what's possible. You first have to understand how does the world work, and then you can figure out what you can do with it. Where are the new possibilities? For example, are there processes that you might not have thought were physically possible, but are, or maybe not even conceived of? And if this sounds kind of familiar, yeah, it's basically the Star Trek generation, right? And Harvey Mudd was a great place to be to explore this. I found my time at Harvey Mudd was a lot of work, but it was much more of an exploration than a grind, and was just a great place to do my undergraduate education. My going into lasers was actually in large part from a career discussion with Tom Hillowell. I actually still remember this, that I was talking to Tom as I was getting close to graduating and saying, I love physics and I love the basic aspects of it, but I want to make sure it makes a difference, that it does something. I was thinking of going into fusion, we talked a little bit about various topics, and one thing he mentioned that really stuck in my mind is that there were these people trying to make lasers, but that work with X-rays. And that struck me as very exciting because it combined some of the basic, it combined the useful aspects of physics with quantum mechanics, and was something that really could make a difference. And when I went, my past since Harvey Mudd is illustrated here. I went to Princeton for graduate school, found the East Coast wasn't really my cup of tea, so I went back to Berkeley, which is about as far from the East Coast as you can get, figuratively and literally, then took a faculty position after graduate school at Washington State University, University of Michigan, and finally in '99 moved to the University of Colorado. There's an institute there, GILA, which is well known for atomic and molecular physics. And one thing that happens as you move around a lot is you tend to accumulate things. So when I left Harvey Mudd, I left in a VW bug. This isn't my one, but it's exactly what my bug looked like. Drove across the country to Princeton, By the time I made my last move, which was 15 years ago, it was 2 semi-truckloads full of laser equipment, basically. And but the most important thing I picked up along the way was my wife, Margaret. She's in the back there. Wave. And Margaret and I run a joint research group. So we met in a lasers class, very nerdy thing, right? But we've been working together ever since, and it's through 3 different faculty positions now, and it's been a real thrill. And this is where we are now, which is that we have a joint research group at the University of Colorado, and we have a couple of dozen people in our group. It keeps us busy and then some. But Boulder's a great place to be and a great place to go to grad school if any of you are contemplating that. We've had some Harvey Mudd students and welcome more of them. The other thing that I did starting in my spare time but has grown considerably beyond that is a company that allows us to make the technologies that we develop more readily available to researchers. So we have about 35 people in the company now, and we make lasers, and the type of thing I'll tell you about. There's even one at one of the labs here at Harvey Mudd. They're lasers that make very, very short pulses of light. So now I'll tell you a little bit about that work. First of all, just to motivate it, the laser is a device that's really transformed science, technology, and society. Everything from surgery with lasers to the internet. The internet is all powered by laser communication technology. The work that we do with making very short pulses of light is a direct descendant of that original work in communications. But now we're roughly 1 million times faster than what the internet uses in terms of speed. But in 2010, it was the 50th anniversary of the first laser. Actually, the development of lasers and the development of Harvey Mudd College were very much along the same timeline. And, you know, it is a great example of useful new basic physics that really has made a difference. And that's why it was an exciting thing for me to go into. X-rays were a transformative technology. And X-rays have been around for a little bit longer. The first X-ray tube was developed by Röntgen in the late 19th century, and this is a pretty famous picture of his wife's hand, and that isn't a tumor there, that's her wedding ring on the one finger. But, and you know, we all know they're useful for things like security at airports and for medical diagnostics, but also the structure of DNA was discovered by using X-ray diffraction. So it's had a huge impact on both basic science and on technology. Lots of Nobel Prizes having to do with X-rays, also a number of them to do with lasers. But the X-ray tube is basically an X-ray light bulb. It's incoherent light that emits like the lights up here in all directions. And imagine what you might be able to do if you had coherent X-ray light. In other words, light like the light from this laser pointer that's directed. And that was what motivated me to go into this work. My PhD thesis work was on developing a laser at very short wavelengths. It was successful work, but is now completely obsolete. But what's the difficulty in making an X-ray laser? Well, lasers rely on storing energy in excited states of atoms. This is the fun part because, Harvey Mudd, we all have this common language where we know what atoms are and excited states and things like that. I won't get too technical, but it's fun that I could put a little bit in there. Like E equal h nu, which is the photon expression. Many of you might not have dealt with it for a while, but you probably saw it in your basic physics class. This relates the frequency of a light wave to the energy quantum, the photon that's related to it. X-rays are light at very high frequency, which means a high photon energy. That means highly excited states very far from equilibrium. That tends to have a short lifetime. And what that means is you have to put more and more energy into a system to make a laser work. You have to get atoms into the excited state to make a laser. The basic physics of the laser was actually first described by Einstein in the 1920s. The laser wasn't invented till 1960. And for me as a laser person, this is one of the very biggest missed opportunities in society, is that we could have had lasers 30, 40 years earlier, and Einstein missed this. So I'm kind of mad at him when I get in a bad mood, but it's because Einstein was really looking at the basic physics, and he needed a little bit more of this, like, what are we going to do with this physics to do something different? But the physics of the laser process is something that you can go through, and it's a junior level physics, and eventually you can derive a power scaling law for how much power you need to make a laser work as a function of the energy of the photons that come out, or the frequency of the light. And it scales as the photon energy to the 5th power, roughly, which is a very punishing scaling. So what that means, for example, is that if you can make a visible wavelength laser that's powered by batteries, if you want that, this is emitting light at roughly half a micron wavelength. It's actually a 1 micron laser that's frequency doubled, and I'll tell you a little bit more about that. If you just take that as the baseline and start scaling to make coherent light in the X-ray region of the spectrum, a wavelength of 1 nanometer is called soft X-rays. That goes from, from 1 milliwatt power requirement to about a terawatt power requirement. A terawatt is roughly the US electrical grid. So that's a lot of power. If you wanted to make real X-rays, would be around a petawatt or so. Now those are incredibly high power levels. It's remarkable that we can generate these now with today's laser technology, and I'll tell you just a little bit more about that. But first, I wanted to give a little bit of history in X-ray lasers. So I graduated in the 1980s. I know there are a lot of people from my class that have showed up. We all know about the Reagan era and Star Wars, the Strategic Defense Initiative. Well, SDI, the origin of that was a group of scientists at Livermore who looked at the scaling and decided they wanted to make an X-ray laser, and that the way to do it was to use as much power as you could get. And at Livermore, that means an atomic bomb. So they came up with schemes for using atomic bombs to power an X-ray laser. And I don't have a clearance, but I do believe that these were successful experiments. They may not have been practical experiments, but they were successful. Practical wasn't a big word at Livermore back then. But that is the origin of the Star Wars program, is the desire to make an X-ray laser. So where are we now after this? Well, first of all, we've done a little bit better than that using large-scale apparatus. In 2009, the SLAC accelerator lab outside of Stanford was converted to an X-ray free electron laser. And this isn't work I'm involved in, but basically you can make lasers using electron beams. Doing that, you do a little bit better than this fifth power scaling. So they were able to make very short wavelength, coherent laser-like X-rays with this device. This is a picture of the device. It is the SLAC linear accelerator, which is 2 miles long. So it's still a $1 billion device, but it does its job, and it's really productive in science. The light emission is due to oscillating electric charges. You probably remember that from an E&M class. Rapid acceleration with very fast-moving electrons gives shorter wavelengths. An alternative is to use a technique called nonlinear optics, and that's where you take laser light and you convert it from one color to another. And this is a process that, for example, this laser pointer uses. You see green light coming out of it, but it's actually an infrared laser that's frequency doubled with a crystal. And what we do in our work is to, and actually this is just the data from the first paper demonstrating this frequency doubling technique. The idea here is at the bottom, this is supposed to be the experimental evidence of second harmonic generation in physical review letters. What they did is take a ruby laser, focus it into a piece of quartz, and then separate the colors out with a prism. Well, what they saw was a little bit of blue light here, along with the red light from the ruby laser, and they published this photographic plate with the evidence. The only problem is that the second harmonic is not here, and that's because the typesetter thought it was a piece of dust and whited it out. So there's no experimental evidence of this process in the first paper demonstrating it. But this is the process that we've now taken to an extreme using pulses of light that are very near the fundamental limit. So we use this nonlinear optics process. We start with pulses about 10 to the minus 14 seconds in duration. That's only a few oscillations of the electromagnetic field and only about a 50th of the thickness of a human hair. So what I mean by that is light moves at c, and the duration of this light pulse in space is about a 50th of a human hair. We take those pulses, we amplify it, and since power is energy divided by time, these very short time scales allow us to generate terawatt peak powers using tabletop lasers. This is a picture of the laser, the first laser that we developed that allowed us to generate these 10 femtosecond pulses. And this is very much like the one that's in the teaching labs here at Harvey Mudd. Well, what happens when you take that light, focus it to very high intensity onto some atoms? Well, what you see is you see the laser passing through, but you also see colors of light that are the harmonics of this. It's basically a coherent process that combines 2 or 3 or 5 or 500 or 5,000 photons from the laser and gives you one very high energy photon. And essentially this gives you a light beam that looks like an X-ray laser. You made a visible laser and you converted the light to a different color, but the characteristics are those of a laser beam. Now, the high harmonic generation, where you see these large number of harmonics, it's kind of like turning the knob on your amplifier up to 11, and you get a very distorted sound. Well, that distortion is the higher harmonics. And we're doing that with light and generating very high energy photons. The reason that happens is that you're actually ripping electrons out of atoms and then slamming that electron back into the atom to generate the X-ray. And the reason this is a really cool process and a lot of fun is that, it does involve this convergence of quantum physics and classical physics. You have a quantum tunneling process of the electron coming out of the atom. You then can basically solve Newton's second law and figure out what the energy of that electron is when it comes back to the atom from which it was ionized. And then there's an electrodynamics of the interaction of that electron with its parent atom. And the reason that the beam comes out coherent is because every step of this process is fully coherent and deterministic. You start with an atom in its ground quantum state. You remove an electron from the atom and put it back in a fully coherent way. What it really is it's a coherent version of the X-ray tube that was first invented in 1895. You're driving the process with a laser rather than just a power supply. At this point, I think I'm running out of time, but the work that Margaret and I have done is to basically solve the challenge of phase matching of this process. And the basic, it's a little bit involved, but the basic idea is that as a laser propagates through this medium, you have to make sure that the laser light and the X-rays travel at exactly the same speed. That way you get constructive interference of the beam as it passes through the medium, and that's what gives you the best efficiency in a really useful light beam. So at this point, our most recent work we published in Science this year, where we showed that we could generate coherent light with photon energies above 1.5 kiloelectron volts, and that does correspond to about 5,000 photons that coherently combine together to give each X-ray photon. It's a new record for nonlinear processes, and it really opens up a lot of interesting new science in this area. So this is just progress as a function of year and what the energy of the photons we can generate with this process. As you can see, there's been a lot of progress in recent years, but now we're actually in the same wavelength range that those guys who used a bomb were doing for coherent light. And we don't have to use a bomb, which means that we have a practical way of doing this, a safe way of doing it. And just to wrap up, we've done a lot of interesting science with these sources. Part of our group figures out how to make the X-rays. The other part figures out what to do with them. The real application of this is in nanotechnology. Very short wavelengths give you the ability to see very small objects and also see very fast moving objects. And that's what we're working on now. And just one final example, for example, we've used this light to make a record tabletop microscope resolution of 22 nanometers, which is right in the range where the most advanced microelectronic devices are right now. And we're hoping that this technology plays an increasing role in advancing technology. This technology also, you can generally, basic phenomena to broad application is roughly a 50-year time scale. And a good example of that is NMR, which was first discovered in the 1930s, and in the 1980s was the first commercial magnetic resonance imaging devices. And I really hope that this technology can follow a similar path, at least to date. This is about 30 years old, this technology, 25 years old. To date, it's really following a similar path. So we can hope that maybe it becomes as useful as that technology. And just to finish up, one thing that's definitely in common with NMR is I found on the web this picture of the very first commercial NMR spectrometer from Varian. And there's a blow up there of the little sign that's posted on it. Bleeding edge technology doesn't change. And of course, now we're trying to sell devices that are commercial, and it's not always easy, but we're doing our best. And so with that, I'll conclude. Thank you very much.